The weight of 400 mcm copper wire is 14,780 pounds per 1,000 feet. The weight of 400 mcm aluminum wire is 4,920 pounds per 1,000 feet. The weight of 350 mcm copper wire is 12,780 pounds per 1,000 feet. The weight of 350 mcm aluminum wire is 4,260 pounds per 1,000 feet. The weight of 500 mcm copper wire is 18,210 pounds per 1,000 feet. The weight of 500 mcm aluminum wire is 6,070 pounds per 1,000 feet. This information can be found in the National Electrical Code, specifically the 2020 edition, Table 8. It is important to consult the National Electrical Code for the most up-to-date and accurate information on conductor properties, including weight. Understanding conductor weight is crucial for various electrical engineering calculations, including determining support structures, calculating shipping costs, and assessing the overall load on electrical systems. The weight values provided are per 1,000 feet of wire length. To determine the weight for other lengths, you will need to perform a proportional calculation. For example, to find the weight of 500 feet of 400 mcm copper wire, divide the weight per 1,000 feet by 2. This gives you 7,390 pounds. Similarly, to find the weight of 2,000 feet of 350 mcm aluminum wire, multiply the weight per 1,000 feet by 2. This gives you 8,520 pounds. When working with electrical conductors, always refer to the relevant codes and standards. These standards provide essential information on conductor properties, installation practices, and safety requirements. The National Electrical Code is a widely adopted standard in the United States and is updated regularly to reflect advancements in electrical technology and safety practices. In addition to the National Electrical Code, other standards such as UL 83 and ISIS-93-649 provide information on specific types of conductors and their properties. UL 83 is the standard for thermoplastic insulated wires and cables, while ISIS-93-649 is the standard for concentric neutral cables rated 2001 to 35,000 volts. These standards can be helpful for understanding the characteristics of different types of conductors. It is important to note that the weights provided are approximate and may vary slightly depending on the manufacturer and the specific construction of the conductor. Always consult the manufacturer's specifications for the most accurate weight information. Factors that can affect the weight of a conductor include the type of insulation, the number of strands, and the stranding configuration. For example, a conductor with a thicker insulation layer will generally weigh more than a conductor with a thinner insulation layer. Similarly, a conductor with more strands will generally weigh more than a conductor with fewer strands. The weights provided are for bare conductors, meaning they do not include the weight of any insulation or jacketing. To determine the total weight of an insulated conductor, you will need to add the weight of the insulation and jacketing to the weight of the bare conductor. The weight of the insulation and jacketing can be obtained from the manufacturer's specifications. When installing electrical conductors, it is important to consider the weight of the conductors and to provide adequate support. The support structures must be able to withstand the weight of the conductors, as well as any additional loads, such as ice or wind. The National Electrical Code provides guidelines for supporting electrical conductors. These guidelines specify the maximum spacing between supports and the types of supports that are required. It is also important to consider the weight of the conductors when sizing raceways. Raceways must be large enough to accommodate the conductors and to provide adequate space for heat dissipation. The National Electrical Code provides guidelines for sizing raceways. These guidelines specify the maximum number of conductors that can be installed in a raceway of a given size. In addition to the National Electrical Code, other resources, such as handbooks and online calculators, can be helpful for determining conductor weights and sizing raceways. These resources can provide more detailed information and can help to simplify the calculations. Understanding the weight of electrical conductors is an important aspect of electrical engineering. By understanding conductor weights, you can ensure that electrical systems are properly designed and installed. The National Electrical Code and other standards provide valuable information on conductor properties and installation practices. Always consult these standards and other resources to ensure that you are following best practices. The weights of conductors are also used to compute the pulling force necessary to install cables in underground ducts or cable trays. Excessive pulling force can damage the conductor insulation and reduce the cable's service life. Therefore, knowing the weight of the cable is essential for determining the maximum pulling force that can be applied without damaging the cable. Furthermore, the weight of conductors plays a role in calculating the sag in overhead power lines. Sag is the vertical distance between the highest point of a suspended cable and the lowest point. Excessive sag can reduce the clearance between the power line and the ground, which can create a safety hazard. The weight of the conductor is one of the factors that determines the amount of sag in a power line. The heavier the conductor, the greater the sag. Other factors that affect sag include the tension in the cable, the temperature, and the length of the span. In addition to the weight per unit length, the overall diameter of the conductor is also important. The diameter affects the ampacity of the conductor, which is the maximum amount of current that the conductor can safely carry. The National Electrical Code specifies the ampacity of various conductors based on their size, material, and insulation type. The diameter of the conductor also affects the amount of space that it occupies in a raceway. The National Electrical Code specifies the maximum number of conductors that can be installed in a raceway of a given size based on the cross-sectional area of the conductors. When selecting conductors for a particular application, it is important to consider not only the weight and diameter but also the other electrical and mechanical properties of the conductor. These properties include the conductivity, tensile strength, and corrosion resistance. Copper is a highly conductive material and is often used for electrical conductors. Aluminum is less conductive than copper but is lighter and less expensive. The choice of conductor material depends on the specific requirements of the application. Tensile strength is the ability of a conductor to withstand tensile stress without breaking. Corrosion resistance is the ability of a conductor to resist corrosion in a particular environment. Conductors that are exposed to corrosive environments, such as saltwater or industrial fumes, should be made of corrosion-resistant materials. In summary, understanding the weight of electrical conductors is crucial for various aspects of electrical engineering, including designing support structures, calculating pulling forces, determining sag in overhead power lines, and selecting appropriate conductors for specific applications. The National Electrical Code and other standards provide valuable information on conductor properties and installation practices. Always consult these resources to ensure that electrical systems are properly designed and installed.